is an important question because that would be a source for rapid. It's not a very big basin, you know. It doesn't take a lot of water to fill this small. It's a small basin, small fluvial lake. Fluvial just meaning cooler and wetter climates. A lake that filled during cooler or wetter climates. Sort of more or less synchronous with the glacial periods in the mountains. Not around here, but maybe in the Sierra, if you can think of. And so the lake levels fluctuations too, you know, we think that there's probably a sill controlling the lake levels in some places. I mean, the sill is spill to and then spill over to a top and go downstream and into lower areas. So that's what when we say a sill, that's what we mean. It's at the bottom, the south end of the basin. It's a spillover point, the sill. One thing about the way that the guidebook is tried to be organized, and that's when there's stop descriptions and some short stop descriptions. When the stop descriptions were fairly short, I included them with, you know, within the road log part of it, which is the first part of the thing. But most of the descriptions that people had, the stop leaders had, were fairly lengthy, and so I put them in appendices, and they're referred to as in the initial stop descriptions. When you get to the stop, it'll say what are we gonna do. And it says, and then it'll have the appendices that you can refer to flip to in the back. It doesn't have the page numbers, but you can go to the table of contents to get those. Why are you laughing, Jay? Jay, by the way, runs the web server, and so a big thanks to him for that. That was a big task this time around. Yeah, thanks. You did a great job. Yeah. I hope, you know. Yeah.
Ooh.
Okay. Is that working? Yeah. All right. So John asked me about 3 days ago to come in and talk about the tectonics of the basin. Sorry.
Did you screw something together?
Yeah. So I printed out a couple of quick maps, and I'd like to just tell you sort of what I was thinking when I described this thing, the Tacopa Hump down here. I had the pleasure at the time of working with Roger Morrison back in the mid-90s. I was working on Proterozoic rocks up in the Kingston Range on the skyline there, and it was a couple of particularly early winters, so I started coming down and spending my time here in the basin and got to know Roger and started thinking about the question of Tacopa Lake. And of course, from my background, I came to it from a tectonic perspective. So I'm not going to talk real long here, just give you kind of the my quick thoughts on what's going on. I know that there are a couple of people here who may not agree with me. I'll be happy to pull out the maps and lay them on the hood of a truck, and we can talk about it in more detail later. What's neat about the finger? Yeah, that wrist. Okay, so this is a simple physiographic map of this region, centered on the Tacopa Hump.
It's moving, which is
located right here.
Whoa!
Again, you probably know this region as a domain of, or think of it as a domain of normal faults and extension, and if you follow the work of Wright and Troxel, you know about some of the strike-slip faults. And there are some really nice models that describe how those things work. But if you begin to look at the details and the various ranges, sometimes, and in most cases, the models don't really fit. There are all kinds of problems with that, and we can discuss some of those during the trip here. But that led me to start looking for things that I could use to reconstruct the basin. And I found that the Proterozoic rocks and an unconformity, an angular unconformity in the Proterozoic rocks turned out to be one of the best lines to use to reconstruct this thing. And that's what led me into the Tacopa Hump.
You said no when you're ready for this one.
Okay, sorry.
We'll hold it up. We'll hold it up when you're ready.
Okay, this is good. All right, just to orient you, again, we're located right here. The Garlock Fault comes in like this, a well-known fault zone, and the Death Valley Fault Zone here, but also a well-known fault zone. Most of my mapping work was over in this terrain, here encompassing the Shadow Mountain region and the Kingston Range and the southern Nopause. And what I put together over here in this region that is still at the moment, because I haven't published enough of it, is kind of terra incognita. But what I think is happening is there is a large
northwest trending right lateral fault system that comes up through this region, through Shadow Mountain, the Shadow Mountain Basin, and that's on the south side of the Kingston Range. At the same time, in roughly coeval, again mid to late tertiary, there is a left lateral fault that comes in on the north side of the Kingston Range. This one is northeast trending left lateral. And they meet in the Alexander Hills, this low range of hills in the foreground. And what's happened is...
That's a real close foreground. Those are the Hot Spring Hills.
Yeah, the Hot Spring Hills are the nearest hills, and then above that is the Alexander Hills.
Skyline south of Kingston Range.
So I have a closer map that we can look at again later, but it's hard to see the detail from there. But what I think has happened basically is that this right lateral fault out of Shadow Basin has been offset by the left lateral fault. They're mutually cross-cutting, so there are all kinds of mixed up relationships in here. The fault from Shadow Basin goes out as the Southern Death Valley Fault Zone, and the left lateral fault on the north side of the Kingston matches up with the Garlock Fault over here. But this little patch in between is just a train wreck. I described it once in a talk as a train wreck. And at another point, John didn't like this. I described them as disarticulating faults. But the net effect where these faults meet and cut off is they create a zone of transpression where we get some shortening. And so what's happened in this is this portion that was a basin has been inverted, and the Tacopa Hump is rising in the very latest part of the tertiary. And because of the nature, the tectonic nature of it, it's coming up very slowly, and the brecciation is distributed through the bedrock underneath. The bedrock here has been through two fault zones. It's been cut off by a left lateral fault that has a minimum 25 kilometers of displacement, and that's spread across a zone about 10 kilometers wide. It meets a fault that comes up from the south that may have as much as 40 kilometers of displacement, and that one is 25 kilometers wide. So the place where those two zones overlap, the rocks have been doubly deformed, and they're intensely brecciated. On Sunday, you can look here, you can see these nice blocky mountain ranges with beautiful stratigraphy. On Sunday, we're going to go down to a place down along the Everglades River, and we can see a thing called Rainbow Mountain. And Rainbow Mountain is the same rocks, but it's completely pulverized. The stratigraphy is still intact, more or less, but it's pulverized. And so the argument is that those rocks, those pulverized rocks that form the basin of the sun, are deformed in a quasi-ductile way. At a grain scale, it's brittle, but when you take the aggregate behavior of this crushed rock mass, it can deform in a more plastic or quasi-ductile way. So it's rising as this big broad anticline, or antiform. Again, it's pretty complex inside, so that's why I went with the hump instead of an anticline. And it allows it then to rise, and I think it formed a sill on the bottom of that created the basin that held Lake Tacopa. So it's sort of the latest tertiary to quaternary structure that evolved and helped create the Tacopa Basin. Okay, so I think that's probably enough for me to say at this point.